Today in this video, I am going to talk about classical and non-classical carbocation. You know what is the classical carbocation? Classical carbocation in the organic chemistry may simply be defined as the carbocation that are stabilized by the delocalization of pi bond or sigma bond or lone pair of at conjugated site to the carbon bearing positive charge. So the carbon in classical carbocation has only 6 electrons. It is electron deficient and therefore act as an electrophile in chemical reactions. A large number of chemical reactions proceed via formation of certain chemical species called carbocation, in which one of the carbon carries a positive charge with only 6 valence electrons. In these sections, we will study the generation, structure, stability, and activity of two main types of carbocation called classical and non-classical carbocation one by one. So you can see the generation of classical carbocation. You have the alkyl halide. So ionization of alkyl halide in polar solvent. You can see the formation of carbocation. Then protonation of alcohol followed by dehydrations. You can see the formation of carbocation. Then protonation of unshared unsaturated system. Then you can see the formation of carbocation. Then action of supraacid on alkyl fluoride, SBF5, formation of carbocation. Deamination of primary aliphatic amines by nitrous acid, deaminations. So you can see the formation of carbocation. Now orbital structure of classical carbocation. You can see the angles 120 and orbital structure of classical carbocation sp2 half dash. Now you know the stability of carbocation: methyl, ethyl, isopropyl, and tert-butyl. So tert-butyl is more stable than isopropyl than ethyl carbocation. Now the second case of unsaturated classical carbocation, where the carbon bearing positive charge is directly connected to carbon participating in multiple bonds. You can see the allyl carbocation, benzyl carbocation, diphenyl methyl carbocation, triphenyl methyl carbocation. Now you can see the stability of alkyl carbocation on the basis of inductive effect. So tert-butyl more stable than isopropyl, then ethyl and then methyl. Since alkyl group has an electron donating effect, that is the plus I, the stability of classical carbocation will increase as the number of attached donating groups increase. The stability order of alkyl carbocation based on inductive effect is given here. Now stability of alkyl carbocation on the basis of hyperconjugations. So hyperconjugation effect can be used to rationalize the relative stability of different carbocation. You can see the tert-butyl carbocation of the hyperconjugations. So 3 hyperconjugation structure for methyl groups, total hyperconjugation 6. In case of here, total hyperconjugation 9. In case of this, total hyperconjugation 3. Now, on the basis of stability of alkyl carbocation, on the basis of steric effect, you can see steric effect. Since alkyl carbocation are primarily obtained from alkyl halide with tetrahedral geometry, a link between the steric reliefs and carbocation form can be established. During the formation of carbocations, In such cases, the carbon-carbon bond angles change from 109 degree at highest minute to 120 degree. Therefore, the carbon with bulky group around is expected to get more relief from the carbocationic conversions. The stability order is the same. Now, stability of allyl and benzyl carbocation. You know the stability of carbocation, which the carbon bearing positive charge is adjacent to the double or triple bond, can be rationalized in terms of resonance effect. First of all, let us draw the resonating structure allyl or benzyl carbocation. You can see this is the allyl and this is the benzyl resonating structure. You all know this. Now you have the resonating stabilization diphenyl carbocation and triphenyl carbocation. Now you can see the triphenyl carbocation is more stable than diphenyl carbocation, then methyl carbocation, then allyl carbocation. Now another sequence, if you have such type of carbocation, so this one is more stable than this one and then this one. So stability of substituted benzyl carbocation. Since the carbon is electron bearing positive charge, is electron deficient in nature. Any group with plus R effect will stabilize the system and vice versa. The order of stability of some typical substituent carbocation is given below. You can see the 4-methyl-phenyl-methylium more stable than phenyl-methylium and then 4-nitro-phenyl-methylium. Now, stability of tropylium ion. The cycloheptatrienal cation or tropylium ion is exceptionally stable due to its aromatic character, planar and 4n plus 2 pi electron. According to molecular orbital theory, its delocalization energy is significantly greater than the delocalization energy of its acyclic counterpart. Similarly, the valence bond theory can also explain its exceptional stability of the basis of the resonance as given below. You can see this is the tropylium resonating structure. Now stability of cyclopentadienyl cation. The cyclopentadienyl cation is very unstable due to its anti-aromatic character, planar and 4n plus pi electron. So according to molecular orbital theory, it is delocalization energy is significantly less than the delocalization energy of its acyclic counterpart. So this is the anti-aromatic. Stability of alkoxo alkyl cation. You can see this oxygen is alkoxy alkyl and this is the positive charge on oxygen, here positive charge on carbon. Now stability of acyl cation. You can see the C oxygen have positive charge, now carbon have the positive charge. Just like alkoxy alkyl cation, the resonance will also stabilize the acyl cation as instability of phenyl and vinyl cation. If you have this cation, if you have this cation, if the positive charge is on the double bond carbon atom, the system cannot be stabilized because the sp2 orbital carrying positive charge will be perpendicular to the orbital of the double bond. Now reactivity of classical carbocation. Nucleophilic attack, you can see here the 50-50 racemization products. Proton removal, you can see the proton removal. Now you can see the rearrangement 1,2 methyl shift, 1,2 methyl shift. Now you can see the addition reactions. Now non-classical carbocation. Non-classical carbocation in the organic chemistry may simply be defined as the carbocation in which the pi bond is not conjugated with the carbon bearing positive charge and get stabilized by neighboring group participation by pi or sigma bond. So generations of non-classical carbocation, your neighboring group participation by pi bond, you can see here positive charge. Now this neighboring group is taking participation and forming 3-member ring. Neighboring group participation by sigma bond, you can see the OBS removed and then the formation of this, and then there is a formation of this two product XO or endo. So this is the orbital picture of non-classical carbocation in 2-norbonyl system. Stability of non-classical carbocation, you can see stability gained via the delocalization of pi bond. You have these products, formation of this and this. Stability gained via the delocalization of sigma bond. You can see the formation of this carbocation and this formation of this carbocation. Now, reactivity of non-classical carbocation, nucleophilic attack, formation of this exo-endo, and if you have this, then the formation of this product or again this product. So, a lot of product here.